Hi everyone, welcome to iacecalculus.com, where we present calculus topics in a clear and concise way. Our goal is to help you think about math concepts and understand the logic behind them. The topic for this video is limits. We won't cover every concept that you need to know, rather we will focus on what's most essential. After you watch this video, we suggest that you review the handout that we posted at the end and work on the problems. Let's start. Limits. So what are the limits? When you think about it, it's something approaches something. And in the definition of the limits, we write, for example, oops, I need the writing. So we write a limit of a function, right? Because that's what we study in calculus. And the variable approaches some number, and let's make it a number. Maybe it approaches 5, and you will see maybe a minus here. What could this minus mean? It's approaching it how?
Well, it's approaching from 1, 2, 3, 4. So
it will be approaching from smaller numbers, right? It's minus, so it's approaching from the left side. Or if I change it into plus, it means we are looking at the values of the function when they are approaching from the right side.
So
and
from
then
9, 8, 7, 6. So we're going backwards.
We're going to 5, and we're trying to get as close as we can. And the definition will say the limit of the function is a value such that as x gets as close as possible to that 5 in our example, the function will get as close as it can to some other value, L. And that's what we say. And it will approach it from left side, from the smaller values, or it can approach it from the right side. If both values happen to be the same, then we say that the function has a limit. And if they're not equal to each other, then we will say that the limit does not exist. So the basic example of the function that will have a limit is some curve like this. And for example, I want to find the limit at this point. Well, it exists because whether you go from the smaller values side from the left, or if you go from the right, you will still arrive to the same point. If you change the function to something, for example, the easiest example will be y equals 1 over x. And let's look when x is equal to 0. Now what happens?
X isn't equal to 0.
X cannot equal to 0, but what if x is approaching 0? What value does the function approach?
When it approaches 0, the y value gets lower and lower. It approaches 0.
Or higher and higher. It depends.
Yeah.
It depends from which side it approaches, right?
Yeah. Mm-hmm.
So what is a limit of 1 of x as x approaches 0 from the left?
Negative infinity.
Yeah, if it comes here, it's negative infinity. And technically we will say it does not exist because it's not a number, but it is negative infinity. What happens if this limit we count from the right side? X goes to 0 from the right side.
Then it will equal just positive infinity.
That's a positive infinity, and we often don't write a plus sign. We can also say that both limits do not exist, but writing positive and negative infinity gives us more information about the behavior of the function. So here's one of the classic examples of counting the limits from one side. We want to figure out this limit when x approaches 8 from the right, right? From x plus. And here's the absolute value in the numerator. What can we do with this? What is the value of 8 minus x absolute value when x is just a little bit more than 8, right? When it's coming to 8 from the right side, it means it's coming from here. It wants to approach 8 from the right side. So what will this expression equal to?
It'll approach 0.
Yes, but if I want to get rid of the absolute value lines, how can I rewrite 8 minus x?
It will be x minus 8.
That's right. So it will approach 0, and I can also rewrite it as x minus 8. Because if I want to know specifically how much it will be at each point as x approaches 8. All right, so let's rewrite it. X minus 8 over x minus 8. And we should write the limit in front. What can we do now?
Cancel them.
We'll cancel them, that's right. And then what is the value of the limit?
1.
And then the value of the limit is 1. That's right. So that was when x approached 8 from the right side. What if I have the same exact problem, but I will change that x approaches 8 now from the left side? What will change? An exact same problem as above. Will it still be equal to 1?
No.
What it will equal to right now?
No, it will.
So
It won't equal 1, because if x is approaching from a smaller number, then we're going to have a negative number in the denominator and a positive number in the numerator. And so it cannot be positive 1.
So we can get rid of the absolute value lines as 8 minus x, because now this is positive. So we can just drop these lines and just keep it as 8 minus x. And then what is the value of the limit? What is 8?
It's going to be negative 1.
Because
8 minus x times negative 1 is x minus 8. So.
Yes, because the quantities are the same, just one of them is positive and one of them is negative. So in this case, it's negative 1. This is a very common type of problems. And we do it by analyzing the movement from the left and from the right. Okay. And when we deal with the limits, there are some common laws of limits, that the limit of the sum of the two functions is equal to the sum of the limits. For the difference is the same thing, or for the coefficient in front. They're kind of self-explanatory. And you will have this chart at the end of the video. All right, so let's do some of the little bit harder limits. So here is an expression. And if I plug in x equals 0, well, it doesn't work. I have to do something. In the easiest case, I can just plug in the value for x and then evaluate the limit. We are not going to look at those because those are basic. We will look only at examples where something doesn't work. Like here, we get 0 divided by 0. So we need to do some sort of manipulation. What can we do here?
Is it approaching 0 like negative 0, or like from the left or from the right?
Well, let's see if it will matter. That's a good question. In some problems that will matter, and in some others it won't.
Okay.
Can we simplify that expression that we have in front of us? Can you divide top and bottom by something to reduce?
By x cubed.
So let's divide it by x cubed. This will disappear, and this will become x to the power of 2, and this will become x to the power of 2. Okay, can you now plug in 0 instead of x? Would that work? So now there is no contradiction. Let me rewrite it so it looks neater. So what we did, we divided by x cubed. because we are allowed to divide numerator and denominator by the same number. And the expression became 5x squared plus 3 over 8 minus 6x squared. And now we can plug in x equals 0. This disappears and this disappears also. So we will have the limit of 3/8. All right.
Yep.
One more of this type. So here in this example, if you plug in 2 for x, you will get 0 divided by 0. So you know 2 is the solution for this quadratic equation and for that quadratic equation. What do you think we can do? We have to get rid of that, of those zeros.
Maybe we can factor.
That's a good idea, because we know for sure that x minus 2 will factor in the numerator and x minus 2 will factor in the denominator, because plugging in 2 makes them equal to 0. All right, what will
so
be left over?
2 times
2x.
It's going to be x minus 2 times 2x.
Well, you might want to look right
plus
here.
Yeah, plus 1.
Plus 1.
Yep. And then the bottom one's going to be x minus 2 times x minus 1.
All right, that's the factored form. So now we can cancel the term that made the expressions equal to 0. And after that, it's okay to plug in the value of 2. You do that, and the top expression, the numerator will become
6, because it's 2 times 3. Plus 2.
But no.
Oh, wait, yeah. 2x.
2 times 2, right?
Yeah.
Order of operations, right? Multiplication first.
That's going to be 5. And then the bottom one's going to equal 1. So
1.
It's going to
So
be
the limit is
1.
5.
Yep.
All right. So you either can plug in the value and it works. And if it does not, in many cases, you can simplify the expressions by factoring and canceling the like terms for them. All right. So let's look at more examples. Here's the next one. Limit as x goes to the infinity of square root of 9x to the 4th plus 1 over 4x squared plus 3. Like this. So here, if you look at the expressions, we're getting infinity divided by the infinity. But how do we know which infinity is more infinity? For example, if it was something simple, for example, x goes to the infinity of x over x cubed, what is this one equal to?
1 over infinity squared.
Yes, so what is that? 1 over infinity squared. 1 divided by something huge. You have 1 apple pie, and you divide it among infinitely large amount of people. How much everyone will get?
0.
0. That's right. So what we get is almost nothing. All right. So sometimes it's obvious, but here the infinities are kind of the same. So the approach in these problems, you look at this expression and see that x is the infinity. Compared to the infinity, plus 1 is nothing. Same thing in the denominator. Compared to this infinity, plus 3 is nothing. And after that, we can work with the new expressions that we can simplify.
Yeah,
Limit x goes.
The top simplifies to 3 times infinity, or x squared, divided by 4x squared. And then we can cross them out and just get 3 over 4.
That's right. Okay, so when we deal with the infinities, we sometimes want to see which one is a bigger infinity. Or like here, if we had lower terms, say in the top expression, if we had x cubed, x squared, we can ignore them because the highest power wins by a lot when we are talking about infinity. And that's the only one we should be concerned about. All right. Then there is a different type of problems where we cannot so easily get rid of the zeros or the infinities. And here's the example. Limit as x goes to the infinity of x to the third over e to the 3x. And you know, e is some Euler's number. It's 3.2 something infinite number. And it is very useful in math. That's not our topic for today. So we'll just keep in mind that it's a number, just like pi, a little smaller than that. All right, so here we have x to the third and some number to the power of 3x, which is an exponential function. Which one do you think will grow faster? And they go towards infinity. So the numerator will be x cubed and denominator, even if I make e smaller, it will be like 2 to the 3x. It's even more than 2. So I can kind of underestimating it, right? 8 to the x. What grows faster, x cubed or 8 to the power of x, if we are talking about really big numbers? Well,
I think
imagine x is even 10. What is
Yeah.
bigger, 10 cubed or 8 to the power of 10?
8 to the power of 10.
Is it much bigger or just a little bit bigger?
It's much bigger.
Yeah.
Yeah.
So exponential function grows much faster. Even if I do like this, 8 to the 10th is huge because 8 squared is 64, and then it's 64 to the 5th power, 64. So something really big. And that's not even infinity yet. It's only 10. As we go further, the difference will become more and more apparent between them. All right, so intuitively here, you know, this infinity is a stronger, bigger infinity, and the limit will equal to?
I mean, if it's bigger than...
Infinity divided by much bigger infinity.
So what would be the proper notation?
What will be the answer if you divide something big by something really, really big?
0.
That's right. So the answer will be 0 because the bottom infinity is much bigger infinity. Okay, so some of the problems you can just figure out without a proper technique, just by thinking about the behavior of the functions. The proper way we can use is called Lapital Rule when, and it's described here, when you have two functions and you have uncertainty like 0 over 0 or infinity over infinity, you can take a derivative of the numerator and denominator, and you can repeat the process as many times as needed. And there are lots of problems where by doing this, you will get the answer. So they will be no longer infinity. And here is the list of the most common derivatives that you might need for this process. So here you'll have to do Lapital rules multiple times, and I'll just write it without limit for simplicity. So if you take the derivative of the numerator, do you know what we will get? It's the power rule, this one. So 3 will go to the front, that's our n, and the power of x will drop by 1. So the derivative of x cubed is?
3 times x squared.
3 times x squared. And the derivative of e is always e to the same power. So it's e to the 3x. However, here there's a chain rule because this is not x, this is 3x. So we have to take the derivative of the 3x. And the derivative of 3x is just 3 because x was to power of 1, 1 moved to the front, and the power dropped by 1, becoming 0. So that's nothing. Okay, so it got better because now we only have x squared in the numerator. Let's take a derivative again. What is the derivative of x squared?
2 times x.
2 times x, very good. At the bottom is the same thing because it did not change. It's still e to the 3x. So it will be e to the 3x times 3. Let's do it one more time because we already have the numerator equal to x. So we'll do the Lapital rule one more time. What is the derivative of x?
Is it just going to be?
It's x to the power of 1. Same rule.
Same rule. So it's just going to be x to the power of 0, which is 1. So it's going to simplify to 1.
So it will be just that coefficient of 2. And the bottom will be e to the 3x times 3 times another 3. So now the numerator is 2, but the denominator is infinity. So the whole thing will become 0 because it's a number divided by the infinity. And there are many examples where you can use the Lapital rule. For example, my final example is limit x goes to the infinity, natural log of 3x over natural log of 2x. So I don't really know what they are. And if I take the derivative of top and bottom, the derivative of natural log, we'll look it up here. It is equal to 1 over x. Well, in our case, it's 3x and 2x. So I will write 1 over 3x times 3, because I have to do the chain rule. It's not x, it's 3x. So I have to take the derivative of 3x afterwards. And then here it's 1 over 2x times 2. And then everything cancels. And what do we get as the answer?
1 over x divided by 1 over x, so just 1.
So the limit is 1. Here we use the Lapital rule. We could have also used the fact that ln of 3x can be written as ln of 3 plus ln of x, and ln of 2x is written ln of 2 plus ln of x, and then
we can cross off ln of ln3 and ln2 because we're adding them to infinity, and so they don't matter.
That's right. They're too small compared to the infinity, and then we'll still get.
They cancel to get 1.
And we'll still get the answer of 1. All right. One other good thing to remember is the definition of the derivative. You can see this by itself on the test when you need to find the limit of this expression. And then you just change this limit into the derivative of x, which you would compute using the rules of the derivatives. You don't need to know too many for the limits. The ones in the chart is all you need, and they're posting it. Okay, let's look at a few examples from the 2012 calculus A/B test that is posted on the website. Here's question number 5. The graph of the function is shown. Which of the following statements is false? This is the function. So first one, we're looking for the limit at 2, right here. Do you think the limit exists? What happens if you approach from the left and approach from the right? Do they match?
Yeah.
They match. So the limit exists. The limit is equal to 2. It doesn't matter that the function has some other value. It's only at one point. So the limit exists and it's equal to 2. Okay. B.
So I think the answer is C then, because if it approaches 4, and if we're going from the left up, then it goes to 4, and if we go from the right down, we get 4, and those aren't the same. So the function has a limit at x equals 4 when x approaches to 4.
Yes, you're correct. And if we have extra time, we can check every other statement to make sure that they're all true. And this is the only false one. Excellent. We also have question 18 on here. Let's scroll to there. Okay, this one, 18. Does it look suspicious, that expression? We just saw it a minute ago. This is the definition of
Could you open?
We saw it right here.
It's the definition of a derivative.
This is the definition of the derivative. So that will equal to the derivative of what function? What is the function here in the example?
Natural log of.
Natural log of. Yes, so the function is ln, and we want it at point
0.
4. The
4.
0 is our little step. What is the derivative? It's the tangent line. We make little step of h from 4, and we compute rise over run. So h is that little step. We make it infinitesimally small, and then it's our perfect tangent line. So that is being calculated at point 4. So it's a derivative of natural log at 4. Okay, and maybe you remember what derivative of ln x is. If not, you can look on the chart. And that's equal to 1 over x.
1 over x, yep.
So the answer here will be
1 over 4.
That's right. Okay, excellent. So that's all that we wanted to cover. The things that are posted are very useful. I want to show you one of the handouts. There is a chart for calculating the limits, and it guides all the different steps that you can take to find the limits with the examples. We suggest that you review this and do the practice problems. There are solutions to them also. If you have any questions, please post them. Bye. Okay, stop sharing.